1.3 Graph of Polynomial Functions. We will look into a guide, okay? A guide that will help us see the characteristics of a polynomial function when we are given only the equation that defines the polynomial function. A polynomial function takes this form, okay? Where n, the exponent, is greater than or equal to 0 and it is an integer. Your coefficients are elements of the set of real numbers, and we saw from our previous lessons that the domain of your polynomial function is the set of real numbers. When visualizing the characteristics of the graph of a polynomial function, it pays to pay attention to the degree of the polynomial function. And when your function or polynomial function is written in the standard way, the leading term is where you will see the degree of your polynomial function and the leading term. So the degree of the polynomial function is the highest integer exponent of a term. And when it is written in standard form, the exponents of the terms are written in descending order. So this one, for example, a constant function is a degree 0 function, a linear function is a degree 1 polynomial function, a quadratic function is a degree 2 polynomial function, and a cubic function is a degree 3 polynomial function. A polynomial function of degree n has at most n x-intercepts. So the x-intercepts are the points where the graph of your function intersects the horizontal axis. Okay? So for example, a quadratic function is a degree 2 function. So that means it has at most 2 x-intercepts. And what does it mean when a function has at most 2 x-intercepts? So it can have 2 x-intercepts. It is possible it has only 1 x-intercept. And it is also possible that it has no x-intercept. Okay? For example, this function, f of x is equal to x squared minus 1. It has 2 x-intercepts. These are when x is equal to negative 1 and when x is equal to positive 1. A quadratic function can also have only 1 x-intercept. So this function, f of x is equal to x squared minus 4x plus 4. It has only one x-intercept, and that is x is equal to 2. But it is also possible that your quadratic function has no x-intercept, such as this, okay? F of x is equal to x squared minus 4x plus 5. It has no x-intercept. So again, when you want to see some inferences about the behavior of the graph of a function, you pay attention to the leading term because the leading term will tell you the degree of your polynomial function. Okay? The degree will tell you the number of x-intercepts. It has at most n x-intercepts. Now, how about this? A polynomial function of degree n has at most n minus 1 turning points. Okay? So a turning point is a point along the graph where the graph changes directions. From going up to going down or from going down to going up. This graph, for example, has 2 turning points. Points A and B, okay? So to the left of A, your graph is going up, and then past A, it goes down. Here, to the left of point B, your graph is going down, and past point B, your function is going up. This graph, for example, has 3 turning points, and these are the turning points. Point A, point B, and point C. How about this? Look at that point. Is point A a turning point? Well, no, okay? Because to the left of point A, your graph is going up or it is increasing, and then past point A, it is still increasing. Point A is not a turning point. This graph has no turning point. So again, we pay attention to the degree of your polynomial function. In addition to the x-intercepts, the degree of your polynomial function will tell you the number of turning points. If the degree of a polynomial function is n, it has at most n minus 1 turning points. So for example, the degree of a polynomial function is 4. So that means it has at most 3 turning points. Okay? It is possible that it can have 3, it can have 2, it can have 1, or it can have no turning points. For example, your polynomial function is a degree 3 polynomial function. So it's going to have at most 2 turning points. For example, okay, so this one is a degree 4 polynomial function. So it has at most 3 turning points. But in this particular case, it has only 1 turning point. Again, this is also another degree 4 polynomial function. But in this case, it has 3 turning points. Points A, B, and C. This one is a degree 3 polynomial function. So it can have 2 turning points, it can have only 1 turning point, or it can have no turning point. In this particular case, this function has no turning point. This one is a degree 3 polynomial function, but in this case, it has 2 turning points. If the degree of a polynomial function is even, the tails of the graph point to the same direction. Okay? The tail ends, okay, or the end tails of the graph point to the same direction. So that means both tails can either point upward or both can point downward. If the degree is odd, the tails of the graph point to opposite directions. So one tail points upward and the other tail points downward. For example, so this one is a degree 3 polynomial function. The degree is odd. So one tail points downward, this part, and the other tail points upward. This one is a degree 4 polynomial function. The degree is even. In this case, both tails point upward. This one is a degree 2 polynomial function. Both tails point to the same direction, but in this case, they point downward. So how can you tell if one tail points downward and the other points upward? Or how can you tell if when a polynomial function has an even degree, how can you tell if the tails both point upward or they both point downward? So what we shall do is we will pay attention to the coefficient of the leading term. Okay? So when the degree of the polynomial function is even, okay, you pay attention to the coefficient of the leading term. If it is positive, the tails point upward. Okay, so both tails point upward. On the other hand, when the coefficient of the leading term is negative, both tails point downward. Now, what happens when the degree is odd? Okay, so again, you will pay attention to the coefficient of the leading term. So if the coefficient of the leading term is positive, the left tail points downward. Now what happens to the right tail? Well, because this has an odd degree, if the left tail points downward, then the other tail points to the opposite direction. It points upward. When the coefficient of the leading term is negative, the left tail points upward, but the right tail points downward. It is kind of intimidating and overwhelming to remember all of this. So what I suggest that you do is you pay attention to the equation that defines your function and pay attention to the leading term. Then pay attention to what does the exponent do to the signs, to the sign of your x, okay? And pay attention to the laws of side numbers, okay? So for example, this is my function. F of x is equal to negative x cubed minus x squared plus x minus 1. The degree of your polynomial function is odd. So right away you know that the tails point at different or opposite directions. One tail point upward, the other tail point downward. But which tail point upward? Okay? So this is what you do, okay? So when the value of x takes on negative values, okay, when you raise it to 3, the product is negative. And then when you multiply it to the sign of the coefficient, which is negative, the result is positive. And so in this case, the left tail of your graph points upward. Okay? Now, if the left tail points upward and the degree of your polynomial function is odd, then you already know that the right tail points downward. Okay? Let us see. Let us see the true graph of this function. Okay. How about this? F of x is equal to negative 2 times x to the 4th minus 3x plus 1. The degree of this polynomial function is even. Both tails point to the same direction. Okay? But this one is negative. The coefficient in the leading term is negative. Okay? And so negative 2 times this, which is always positive because the exponent is even. So the product of this term or the sign of this term is going to be negative. So the tails of your function point downward. This is the left tail and this is the right tail. Okay, so let us show the true actual graph.